can just say just 1 or 2 words about improper integrals. So basically, we want to do a few things in improper integrals, some problems, calculations, and existence. Okay, improper integrals. Okay. So, I mean, the question, if I ask you guys, like, why do we need improper integrals? Yeah. Let's say, so why improper integrals? Why integrals? Integrals because we want to make sense of the notion of area under the graph of a function, or in general, but yeah, so we have integrals. But then why do we need improper integrals? Any ideas? So see, roughly there can be two things. Okay. So one thing is when the domain is not a finite interval. Okay, that's one thing, right? When domain is not a finite interval. Okay, so in this case, we have things like, which are the usually the kind of questions which you see. So let's say we have something like this. Let's keep it like this: 1 to infinity sine x by x dx. Yeah, so this here we need an improper integral, because this is not obviously, I mean, or rather I can say that the range is not, it's not finite. But I'm not, so point is, what does this mean? What does it mean? Because knowing this precisely is half the work in showing improper integrals exist and things like that. This is important work. Important part is to be able to show, I mean, to be able to know what this means. What does this mean? So let's try to understand that. Anyone would like to say? What does this symbol mean? How do you see it? Oh, Adish, no, Adish, you're not audible. I cannot hear you. It's not at all. Yeah. Okay. Okay. Yeah. So area of the function when this tends to infinity. Okay. Anybody else? Sorry, Adish, you want to say something? Yeah. So just to say the same thing more precisely. So I mean, this is not a number as such in the beginning. Okay. It's the limit of something. So it's the limit of what? So we have to go to anything. Let's say some t. And you do sine x by x dx. And this, you see, this is a function of t. Okay. You can call it capital T. Okay. And then what you're asking for is the limit of this as t tends to infinity. Okay. I think it's very important to understand it like this, because then a lot of misconceptions, more than solving questions, a lot of misconceptions can be resolved. Okay. I will try to show that through some examples which I have in mind. But yeah, this is what it means. It's the limit. Okay. And the limit cannot be taken inside, or rather, I mean, doesn't even make sense. Sorry. I mean, here it's t. So it's in the limit is on the oval itself. Okay. So it's the limit of a function. That's what it is. Okay. But remember that it is not some arbitrary function. Okay. This function is the integral of something. There's some echo, sharp echo. Yeah. So it's the, yeah, this limit is not so arbitrary. I mean, if you replace this situation by, let's say, sine nx by x, okay, and let's say you fix this from 1 to 2, and then you take the limit as n tends to infinity. Okay, this is slightly different. Okay, this is more general, because in this case, the inside the functions themselves are changing. The functions that you're integrating are also changing. Okay, in this case, like the function is not changing, but your region, rather your range in which you're integrating, that is changing. Okay, right? So this situation is slightly different. This is integrating, we are integrating a sequence of functions. Okay, we have the sequence of functions, and we are integrating that. Okay, this will be slightly different. We will not be looking at this so much. We'll not be looking at this at all in today's class. Okay, but yes, now I can, yes, yeah. Okay, so that's all. That's all I've said. So can anybody point out where is the other place where indefinite integrals can come in? And that is, sorry, improper. Yeah. No. Right. Yeah. Adish, you wanted to say? Mhm. Yes, exactly. Yeah. When the total range is not under your hand, uh, but as you take the limit, it's well behaved, and so you can approximate the area as accurately as you want by, you know, by letting the range tend to that unreachable, uh, you know, a range of integration. Yeah, so that's what it is. And this is very important because sometimes it will not be explicitly given to you that this is an improper integral or whatever. You will have to interpret it as an improper integral and do it. Okay, or you have to set up the integral, then it's improper, or you'll be clear that, yeah, so just like we saw here, maybe ln x. So this doesn't make sense. Yeah, but you can still, but you can define it like epsilon and limit epsilon goes to 0. It will still not exist. So in this case is not very useful, but in some other cases it's useful. Okay. Yeah, so that's fine. It's simple. Okay. Let's then do a very small example first. Okay. And then we can move forward. So mostly the first part we can, so there are two aspects to these kind of questions. Okay. First is existence. Existence here becomes a tricky question because first of all, whether the function is Riemann integrable on a usual domain like a closed interval, that's number one question, which we have already thought about earlier. But the second is, will the limit exist or not? Okay, so there are two kinds of questions you have to answer when you are answering the improper. So, but that basically I'm putting as one, existence or convergence. This is a very crucial thing because half the time we're not interested in calculating the exact answer, but the convergence. And the second is a computation. But first let's look at convergence. Okay, so let's look at convergence or existence, same thing. Okay. So let's do a very simple question. So how about this? So you have to naturally make the right interpretation and do it. So please do this. Means, as I've said, convergence. So does it converge or not is my question. Okay. So why? Right. And you have to say it in that language of limits. So you have to say that I am assuming that this is the same as t going to 0, t to 1, Okay, this I just gave to just to put the right notations. Right now, from here you can finish it. Right, because in this case you can actually find the antiderivative, and you can actually find the you can find the antiderivative. So you can obviously then find the definite integral from t to 1, and the limit doesn't exist. Okay, so yes, and in fact that is very fundamental, because there is a very sharp there is a very proper comparison that you can make. So we know that, and this is a good integral test for not integral test, a good test for convergence of improper integrals, which draws analogy from summation. Okay, so we'll see. So I'll say, so this is from n to infinity. So maybe I just write k, and then you guys know that this is, or maybe I'll just write t, because that's a traditionally, that's how it is. No, so I don't know what is happening. There's a lot of commotion, so I'm just getting confused. 1 minute. So k from 1 to this. So this is k to the power p. Yeah. And so just quickly tell me, when does this converge? For what p does it converge, and so on? Right. So this is converging for p strictly greater than 1, and yeah, it is equal to infinite. Yeah, so we all know this. Now, the exact same thing holds when you replace the summation by the integral. Okay, the exact same thing holds. So what I'm saying is, you can just replace this. Wait, what am I saying? So the 0 also comes in, right? No, so what did I want to say? I'll just see, because I had it somewhere here. Just messed it up. 1 second. Oh, someone just changes the settings. Yeah, one test. No, so I shouldn't get confused, because converges when p. Yeah, so it's the same thing. So why should I get confused? So you can write the same thing from 1 to infinity. This is converges when p is bigger than 1. Okay, and otherwise it diverges. So uh, proof, can you do the proof of this? So it's easy to guess this, because yeah, but how do you prove this? Or let's say, yes. And then take the limit, and we'll know if it's correct. Yeah, minus p plus 1. Yeah. So yes, and you see, because p is bigger than 1, it exists, right? Because this becomes 1 minus p is less than 0, and so this basically is of the form k to the power p minus 1, where p minus 1 is positive, and so it goes to 0 as t goes to infinity. Okay, so you see, we saw that just the analogous result holds from, from the summation theory. But that's not what I wanted to say. That's why I got confused, because I bought this in the wrong place. uh, what I want to say, what I wanted to investigate, I don't know what is the real thing here, is what if we do from here, then what can we say? Can we say it's finite or infinite? It should be easy to check, so let's just check it. Maybe I'll just write x here. I'm not writing the limit now because it's okay. P plus 1. It is similar, right? And the 1 minus P we can forget this thing. So it will be finite. Yeah. Once again, because P minus 1 is no. Just check, is it finite? So it's infinite. Right, is infinite, right? Because 1 minus, yeah, that's just a small thing, but it's infinite because if you take limit x goes to 0, right, it is infinite. Right. I mean, these are simple things. There's nothing really in this, but you have to just, yeah. But the earlier thing that I said was that's just the analogous result from the summation. And why I'm repeating this several times, because all the tests for convergence in summation can actually be translated. Okay, we will not do that step by all of them. We'll see what we need in the next problems that you guys send me. I'll just do that next, and there I will try to show you what we can translate from that theory of summations. Okay, because no need to give all the results, there's no point. Okay, so yeah, so we know that this one does not converge, right? So this one is infinite, or yeah, it is infinite. Okay, and obviously when you get square here, then it's also infinite. We have just checked, and square root it's finite. We know all that, so it's fine. So these are fine. So these are fine because these are all positive quantities. There's really nothing to do, right? These are all positive quantities. The problem happens when you if you get negative quantities. Okay, and that's when problem happens. So well, there was a question. So what, yeah, the first question was this one, 0 to infinity. I don't have my phone here, but 0 to infinity, cos x, right? Cos x and then cos of x square. Yeah, and then there was a by x, right? Yeah, I think there was a 2 also, but it doesn't matter. Yeah. So here we don't want to compute the integral. I think you just want to check convergence. So you guys tell me first, right? Because this is a problem you would have thought about. Yes. You say, you just, anyone just say, and whatever. Okay. Right. Then yeah, less than equal to, is it true when it's negative also? Okay. So what do you compare this with? So this is less than cos x over x and bigger than, okay, no, that will not work, I think, but let's see. Let's see where it goes. Modulus of this is less than modulus of this. Okay. No, but there is modulus, right? There is a big problem here because that's the kind of question this is. Yeah, so in this case, it can be a big problem. But let's see. So this is Okay, so this is less than this, and can we say that it is bigger than minus cos x? No, we cannot say that. And also it will not be useful because they don't tend to the same thing. No, so in this kind of question, that's the hard part, because these integrals are not absolutely convergent. Okay, so there are two kinds of convergence, right? Those integrals which are absolutely convergent. Okay, so if it's good to have this compartmentalized, maybe in the sense that if mod f fx dx, okay, converges. So I'm just writing less than infinity, so it's understood that the limit exists. If this happens, okay, then what do we say? Then we say that this is absolutely convergent. Okay, means that fx from 0 to infinity is absolutely convergent. Okay, then so I'm not just giving this as a thing, because I'll say something interesting here also. Then this is called absolutely convergent. That's just the name. Okay, but the good thing that I want to say is that this, if this happens, then it implies that this also exists. Do you guys know about this? Okay, but then even then, have you seen this thing in summations at least? Right. So we are saying that if you take the input values in the summation and you mod the input values and then you take the summation, if that thing converges, yeah, meaning that it's bounded, then it does not just imply that this will be bounded, but it also implies that it won't oscillate like in a bad way, but it will converge. That's a non-trivial thing, right? So this is called, and this is important not in this question, because this question is a precise counterexample to that, but it's useful in okay, even I think in this question it will be useful. Let's see, but let's assume this for a moment. Okay, so this is called conditionally convergence implies absolutely convergence, and there is a similar result where we know that if this exists, okay, that it implies that this exists. Okay, I'll just try to discuss the proof in after we do the problem. Okay, because it's also a good exercise. It's a good application of a interesting thing. Okay, this is okay, but let's try to do this question. So, well, so usually the technique in these questions is you break up the domain. You have broken up the domain like this, but I guess that will also work. But let me break up the domain in just a more, I don't know which one is more natural, but anyways, this is usually okay. So we just break it up like this. Okay, you break it up like this, and then you try to do. So can we say which is there any of the is any of the integrals obviously convergent? Why? Hmm. Right. Yeah, but you're taking the summation, right? You're taking an integral. Okay, right. So I don't know. So far, I don't think we can say anything Okay, because because 1 by x also doesn't converge. Okay, so then what can we do? I don't know. So let's try to apply integration by parts. Okay, maybe one part will simplify and the other part we can say. Okay, so let's try that. So let's try to apply integration by parts in this. So yeah, so maybe we can do. Yes, I had worked this out, I think, but now I forget it. Yeah. Anyways, so you do cos x. 1 minute. Okay, so let's integrate cos x. Okay, so that becomes minus sine x. Okay, and integrate means you take the antiderivative. Okay, that's the rule in by parts, right? You take one function, you take antiderivative, not integrated. You take antiderivative, and other one you leave as it is, and then you take the limit of this. So just take this from 0 to 1. Okay. So this one will have no problems. Is it right? That has no problem. That part has no problem. Okay. So this is safe. Let's come to the other part of this thing. So, the other part of integration by parts, we have to take again the antiderivative. So that's minus sine x, it becomes plus sine x. And then we take the derivative of this. So can anybody say what will be the derivative of this? How do you? Because that is already there. So I just leave it like that. And I integrate the cos x. I wrote it in the wrong, I wrote it in the opposite order, right? But usually it's written not like this. Yeah. I don't know what UV, but yeah, I'm integrating this thing. Yeah. Yes. I'm integrating this cos x, and this is my other thing. Okay, fine. Yeah, so you can see, I'm integrating cos x, I'm getting sin x, that's simple. Okay, so again, I integrate the cos x, I should say take the antiderivative. So you take the antiderivative of cos x, so you get minus sin x. So just tell me what's the derivative of this. So this will be x square, okay, and cos x square, we have to take the derivative, right? Sin x square. I can't do, I forgot, I don't know how to do this. Then you do minus, right? And then what do you do? Then you take the derivative of the x, right? And that's just 1, so you have cos x square. Is it right? Oh, good, thank you. So then we have this, and now we should look at this. So now you look at this, you get sin x by x square, 0 to 1. No, we have further things, 2x sin x square minus 2x square. Yes, right, because there is x, another x, right? 2x square, right? But that's good for us because that's finite. Yeah, that is good. So then you have cos x square, sin x, and x square. Okay. So now so you guys can tell me what can we say about this. So you see, this part is fine, certainly. This part is also fine, no doubt. What can we say about this one? Yes. Yeah, it should be positive, right? No, but there is a x square in the denominator, right? Hmm. So then does it work, simplify or anything? Oh, so then it means that it's actually integrable. I mean, you can actually find the thing, right? Uh, okay. So then that is fine, right? Yeah, that usually happens with these kind of functions. But let's actually work it out and see. So yeah. So which one do you integrate? Hmm. Yeah. Yeah. So sine x is cos x or whatever minus sine x. Yeah. I'll agree. Let's assume you are correct and you actually do something and you get something which is integrable and you get this original thing back, right? You're saying. Uh, First one is no problem. If we are not able to find the integral because there are these things which you don't, maybe you can find if you do some work, but there is no problem. Okay, you can. I know. Yeah, so that also you can use. So that's good. Okay. So then let's leave this thing and let's move to the second one and let's think about that. What happens in the second one? Or maybe we should not erase everything, right? Because we have to just change the limits. So yeah, so these things will remain the same if you just change the limit. So what happens to this when you take from 1 to infinity? Still no problem, right? Yes. Yeah, because that one the cos is no, at 1. No, why is it 0? It is not 0. It is 0. No problem, right? Okay, good. Good. So that's okay. That's done. So then we have 0 to infinity. No, it's 1 to infinity. Why am I saying 0 all the time? Yeah. Then we have only 1 to infinity. So then, so once again, I think, yeah. So say, what can we say from here? Let me write it. What we have so far is 1 to infinity sine x sine x square minus cos x square sine x by x square. So think about this part. What is it that we can say? So there is something that we can say very easily, and there is other part which I think is a little bit of work. Okay, so what can we say about the second term? Look at the second term. Look at the second term, the interval of integration also. And you will see that you can say something. So the claim is that that is convergent. And the x square is the key. Yeah, so you guys able to see, so just use comparison, just simple comparison, like similar to what I think Adish was saying for the same term when it was between 0 to infinity. Sorry, 0 to 1. That time it was not working, but yes, yes, right. But here you have to say a few things. So the thing is that, see here, little bit of thing is there, because what you will have to see is you are able to say that mod of this is less than 1. And that is important. If you just say that it is between -1 and 1, I mean, that's also fine, but that doesn't really say the convergent. Okay, I should say this is less than 1 by x square. Yeah, mod of this is less than 1 by x square. Okay, so this, okay, this is true, right? Right, okay. Now, when you take the integral from 1 to infinity and 1 to infinity, then this right part exists, and so the left part will also exist. Yeah, both exist. Why are they existing? Because the integral is bounded. It's obviously increasing function, right? Because positive function integral is an increasing function as you increase the domain of integral. So it's an increasing function, and it's bounded function because the right part is bounded. And so we know that it exists. Now you have to invoke that result, which I was saying, or maybe we'll prove it, try to prove it. This exists. Okay. It is not completely obvious. If it is, then you can tell me that this implies that this also exists. Also exists. Yeah, as this was just the result I was mentioning. I didn't know it will come up in this. It was not clear, but it came up. Okay, that absolute convergence implies conditional convergence and implies convergence. So I think you have to use this. Now, there may be a tricky proof which doesn't use this, but I don't know. You have to show me. Okay. So is it okay? Then we'll look at the other part. So then let's look at the other part. So this is done. We will try to explain the reason for that because I think it's important to explain it. Now let's think about this. So I feel obviously this should also converge, but it's, I don't think that sin x is oscillating, so it may not. I don't know. Let's see, because it's not sin x, right? It's a summation. Okay, so it's a summation, so it might just exist. We don't know. So how do you do this kind of thing? So how do you do this? I mean, maybe you can think about just sine x squared first. So, and then if you get that, that is no, 1 minute. Yeah. So, I mean, what I'm thinking is like, if we can show, okay, if we show that this, no, but that will not exist. No, sorry, that will not exist. So what should we do in this? So maybe we can do some kind of by parts again, okay? But what I'm thinking is maybe we do something like this and then do the by parts. Otherwise, you can try if it works. You could try by parts, but I think if we try by parts with a little bit of thing, something slightly, like just multiplying it, and then because this looks a little more, and also there was a 2, no, but that 2 is not related, I think. Yeah, something like this, then maybe it works, right? Because there is only reason is because this is a integrable. Okay. So then we can just do it. So we get what, sine x, and this is what? Oh no, so is it wrong? What is the integral of this 2x sine x square? That is cos x square, right? Yeah, minus cos x square. Okay, minus cos x square. And you can do this from 1 to infinity. Wait, oh no, yeah, there is an x. Good. Otherwise, you were in trouble, right? So this is again okay, because there's an x in the denominator. It's a similar stuff that we have been doing. Yeah, that's the point, because now it seems like we are coming back to, I don't know what will happen. Yeah, just trying. Yeah, because I don't know a direct trick for this, so that's why it's a little bit of work. But next, so you again get this cos x square, and you get sine x by x by x. No, we have to differentiate that. Yeah, that's good, and that's what we need, right? We need the differentiation there. Then it is good. So if you differentiate sine x by x, you get x square cos x minus x cos x minus sine x, right? You get this, and then you see again here, if you break this up, then it's good, because once again I think similar, this will again converge by the argument we just saw, and I don't know, something happens, and then you get x. No, but then what do you get? You get cos x square by x. No, but you end up with the same thing, and that's not good. That is not good, because it can just cancel, right? And we just get 0 equal to 0. Well, I'll work this out. Or did I work it out? Maybe I worked out the other one. This one I left. It's not here. Yeah, so I thought that I could just complete it from some place, but it doesn't work. So No, so this does not work. So what you guys can try is just try by parts on this and see what happens. Okay. Yeah, so it is not done. So sine x, you guys are getting anything? Yeah, no, but this becomes a difficult question. So it's coming down to this. 1 to infinity sine x square. So this is what I know. So I know this, that sine x square only, if you take that thing, that integral converges. But when there is a sine x multiplied to it, then it can, but sine x is less than 1. No, but that doesn't mean that it will still exist. Okay. So, well, so try to do this problem. This is just this. Can you guys just try this now? I mean, so this exists. I'm telling you that it exists. Just try it. Just a similar trick by this 1 by x that I did, right? Just try to do that trick and see if you get something and tell me. I think maybe not, because that's the problem, is that these terms can be negative and positive, right? Yeah. But just, huh? No, yeah. No, it's not true, because mocks are just made, right? They are made by people and they can give in hard questions. Why not? It's not official exam, right? I don't know. Yeah. I mean, we have made some progress. So we have kind of, we're only here that we are kind of getting stuck, right? Only here in the last thing. And if you try, if you try to do this one, right, then you can see a way out. Okay, maybe. So what I'm saying is that if you try to solve this one, then you will see that this 2x sine x squared dx, yeah, this may be a bit, but I don't think that just comparison does not work for these kind of questions. Just even the next question which you gave me, sine x by x, yeah, just comparison doesn't work for sine x by x. I can tell you that. Okay, because okay, yeah, but you see, we also used, sorry. That's the thing, because of the mod, and the mod is because, and I'm trying to do it rigorously. Like obviously, if you build a little non-rigorous, then we could have done this problem some time back. Okay, but we are trying to do it rigorously. So, anyways, let's see. So if you have this thing, then let's just see. So again, the first part will be simple, like the integration by parts we will apply. Let's just look at the second part. So what happens in the second part is this. See. So you get 1 to infinity. You integrate this thing and you get what? You get cos x square. But then something very interesting happens. What is that? Agreed. Yeah, you take the derivative of 1 by x, you get this. Okay, now you see, I could have started with mod of this. Okay, no problem. Mod of this, no problem. Right. And I mean, right. What to put the mod here? 1 minute, 1 minute. No, 1 second. So mod of this, but then with the mod, you have to split the integrals. Second. No, so that's not a problem, I think, because I mean, you can just split the intervals, right? I'm not really using any comparison. Okay, I'm not using a comparison that something is less than something so far. Okay. Okay, so what I'm doing is if you take mod of this sine x square, okay, even then, yeah, even then you can see that this happens. Right? Because for the x, there is no problem. It's from 1 to infinity, right? And yeah, now we know that this is less than integral 1. Yeah, is this, which converges. Okay, so you see this sine x square is the mod of sine x square is converging. Okay, so what I mean to say is that if you take this, yeah, mod of this is less than no. So mod of this is less than or equal to mod of this. Okay, and this thing is converging. Yeah, I mean, so mod of this integral is, sorry, I can't hear you. Left hand part. Yes. Yeah, because its modulus is less than something, and it is also its modulus is less than this, and it's converging, and this is converging. So this is converging. I mean, it's integral, and so this should also converge. Right, and hence I am able to say that answer is yes. But one has to still see if there are any gaps. Ah, okay, yeah. So that is a thing. But there is a little bit of, I think, non-rigorous thing here, because see, mod of, I can say that, 1 minute. So if I take mod of this, then this is certainly less than this, but not without the mod. No, this is wrong, because if I keep the mod here, then this is fine, and that part will be fine. But if you take mod of sine x square 2x, then Yeah, that's fine, right? You can say that is cos x square, mod of cos x square, because you will have the sign in the intervals is positive, negative, and you can do it, I suppose. Right, so it seems to work. It seems to work, okay? So this is a little tricky question then, I would say. I don't know. Yeah, it seems to be a little tricky to me. Okay. But we did learn a few things. That's fine. Let's just quickly look at this thing. Why this thing just yeah, let's just look at this thing. So because it is true as a fact, but I don't know the proof of this. Any interval mod fx, it should be fx dx converges. This implies that, because it's a remarkable fact, right, also converges. Right, so let's see. Yeah, so if you take the integral from 0 to t, and if you call this ft, okay, then you're just looking at the limit as t goes to infinity. Okay, but I will not, but it's hard to show that that limit exists, right, just by knowing that that other limit exists. But what we can look at is we can look at the difference. Okay, what I'm saying is you look at ft minus fu, some other u. Okay, and if you look at this difference, and maybe you can look at the modulus of this difference. Okay, then what is this? This is u to t, right? Or maybe if you can say that t is less than, or u is less than t, whatever, it doesn't matter. Yeah, then it is from u to t. Modulus is outside here, but we know that this is less than, yeah, you can take the modulus inside. Okay, and you see by the definition, this is where yes, right, because this limit exists, you know that you can make this less than epsilon. Yeah, that's the meaning of yeah, you guys agree? Because yeah, is it fine? So think, then if I need to, then I will say. Yeah, I'm sure that is correct, but you have to see if it makes sense to you. So this will be mod on dx, not on dx, mod on fx. Yeah, so then you have to, no, that is not less than an epsilon. In fact, that is going to infinity. We let t and u go to infinity. But no, the problem is that the point is that if we know that limit of no, so let's not introduce any notation. Because this is less than infinity, what does this mean? Yeah, this means that there's a limit L, right? There is a limit L to this L, right? This means that given any epsilon, yeah, you can find delta, you can find L, small l, let's say, such that integral from 0 to L of, yeah, that's what it means. That's what limit means, right? That this is less than epsilon, right? For all L bigger than some k. For all L bigger than the k, some k. The limit goes to L, capital L. Okay, that is just definition of limit. Is it okay? Yeah, and then you see you can take another, I mean, all L bigger than K, right? So you take L, you can take T, you can take T, and you can take U again, and you can take the difference. It will be less than 2 epsilon or something like that, right? Or you can take, yeah, some, maybe, whatever, yeah, you can. Okay, you get U to T. Yeah, similar, because, so just to say it, you similarly you will get this thing minus L again less than epsilon, and then you can add these two and you can get that. Okay, so that's what I'm claiming. That is what I was saying, that's the case. Yeah, and this is the exact same type of route that one takes when one proves the same statement for summations and convergence of series by using absolute convergence. So we know this. So what do we know? We know that integral u to t fx dx is less than epsilon. Yeah, and this is true. I should write more. Is for all u and t, for all u and t bigger than some k. Given epsilon, there exists a k that depends on epsilon. So I'll write k of epsilon. Given an epsilon, there exists a k bigger than an epsilon, so that beyond that point, the area doesn't change by more than epsilon. That's what we are getting about f. Okay. Now you can use this to show that limit when f goes to infinity actually exists. Okay. This is now, it has nothing to do with integrals. Nothing to do with integrals, right? It has absolutely nothing to do with integrals. F is a function, and you have shown this Cauchy criteria. This is a Cauchy type criteria, right? Given epsilon, you are making the tail less than epsilon. Yeah. Yes, that's right. The terms are getting closer to each other. Yes, and that it's like, yeah, and in a very in a very precise way, they're getting closer to each other. So how would you prove that this, you have to show that this implies that limit, I mean, it's not trivial from here. I mean, it's not completely obvious, right? Somewhere it looks intuitive, but it's not obvious. So this implies that this exists. Okay. So this is a good question. Maybe you can treat this as a homework and try this. You can use Bolzano-Weierstrass. Every sequence has a convergence subsequence, or every bounded sequence. Yeah, because from here you see that f is bounded. That's obvious. At least that you can see, right? That f is bounded. That should be immediate, because you can just let, I mean, one of the t, you can just fix one of the t, just fix the u, just fix it, and as t changes, and it's t bigger than k epsilon, it's bounded, it's clear. F is already bounded, you have proved. It may not be monotonic, but you have to show that it converges. So you take a subsequence, and that will converge because it's bounded. Take another subsequence, that will also converge, but they have to converge to the same place because terms are getting closer. That's a kind of argument, but this is not a proof. You have to write a proof. Okay. So this is a good, very good thing. Okay, so you should not miss it. Okay. So yeah, that's what I want to say. Let's do the next problem. For the next problem, I will just give a small hint that if you just introduce a parameter, that's a standard this thing. So okay, are there any questions here? Just see and note down if you need to think about something. because this is the what we learn. This is the learning point, maybe. Yeah. Okay, so then let's move to the next problem. I'll just give a small hint, okay, because yeah. So so what was it? So we wanted to find this. Let's not get too much into the existence. Okay. Yeah, this is the thing. I mean, existence, as I am saying, you can just prove again by parts and so on. It's simple. Just do by parts. You will get the same kind of 1 by x square kind of thing. One part will be simple. One part will be like 1 by x square. You can do that. The mod of that is convergent. Okay. And so this will be convergent. So that part is simple. This thing now about the calculate, because here we have to calculate. It's the standard limit. To calculate it. Yeah, so we usually we control this function, the oscillation of the function we control by introducing another parameter. Okay, so just use the standard notations. Okay, so the parameter that is usually introduced is some s, but obviously that s has to be related to x. Okay, it has to, yeah, in a sense we just do this sx. It's just a new parameter that is introduced. Okay, 0 to infinity, and this thing is again the standard notations. This. Okay, so now you are looking, basically you're looking at the right thing now. You're extended the picture so that now it's a complete thing. It's a better thing. You're looking at it as part of something where you can make sense of it. So this, yeah. Now the standard way to do this is you first differentiate this. Okay, you first differentiate this with respect to s. Okay, then what happens is you get a simpler function which you can easily integrate with respect to x. Okay, and then in that answer you just put s equal to 0. Okay, that's the idea. You introduce a parameter, okay, and then you differentiate it, and then you integrate it with respect to x. Okay, because when you differentiate this with respect to s, you will see what you get. And don't think too much about the limit. So when you differentiate this with respect to s, you have to differentiate this, but you can take the different derivative inside. Now that, don't go into why that is true. That is accepted. That's not a problem. It's just a differentiation. So basically this you have to differentiate with respect to s, right? So what do you get? So yeah, you can just see it right now. You get this. Basically the x cancels. And then this you can integrate easily with respect to x, right? And right. So when you integrate this with respect to x, you get something. And then maybe integrate that again with respect to s. Right. Then you get I of s, right, the right thing. And then you put s equal to. You can try to work it out, try to see. Okay, this is a good no, this is easy. This is, yeah, this easy. I mean, this you can do, but after that, there are a few steps. You have to eventually find I of 0. You can work out. It's hardly simple. Point is that the function becomes simple when you differentiate it with respect to this parameter. Okay, that's somehow it just works. Okay, there are some other questions here which you can note down. So, where is it? No, not Google. Yeah, I wanted to share this one. Yes, this, yeah. You can just note down these. So I had collected these from some other places in some previous time. These are good variation, or I'll just send it. Okay, you can see all of these are like that. There are some extra parameters already there, and to calculate the integral, you differentiate with respect to the parameter, becomes simple. Okay, maybe I'll just share it now. Okay, yeah. So then that's it. That's it for today. Okay, and